In this video, we are going to learn about JK FlipFlop. JK logic diagram is shown here. These are the expressions which help us to complete the function table. And this is the graphic symbol for JK, which shows two inputs J and K and two outputs Q and Q bar, which are complement to each other. Now, let us put JK values as 0, 0 and observe that it preserves the previous state, that is Q of t plus 1 is equal to Q of t. Substitute the values of JK as 0, 0, and as the logic diagram functions when clock is equal to 1, we are considering clock is equal to 1. Q bar is given as a feedback for this NAND gate and Q is given as a feedback for this NAND gate. And here also another feedback is there, so we are having Q here and Q bar here. Now the inputs of this NAND gate is Q bar 0, 1. So it is like Q bar dot 0 dot 1 whole bar. So it is 0 whole bar will get output as 1 for this NAND gate. Similarly here also, if one of the input of NAND gate is 0, we can directly consider that the output will be 1. So the output of both the NAND gates will become 1. And here you say like Q dot 1 whole bar, that is Q bar, and here Q bar dot 1 whole bar, it is Q. That is nothing but what these expressions say about the NAND gate. So we'll get Q and Q bar here. So we say that when JK is 0, 0, it preserves the previous state, that is Q of t plus 1 is equal to Q of t. And now let us consider 0, 1 case. Substitute the value of J as 0 and K as 1 and clock as 1. Give the feedback Q bar. Give the feedback Q. Now we can see that the output of this NAND gate is 1 and this NAND gate is Q bar. Q dot 1 dot 1 whole bar is Q bar. Now here what happens, Q dot Q bar is 0, whole bar is 1. So the Q bar will become 1. And this is fed back as an input to this NAND gate, and 1 dot 1 in for NAND gate is 0. So Q is 0 and Q bar is 1. So when J is 0 and K is 1, Q of t plus 1 is 0. And now let us consider J is 1 and K is 0 case. And we can show that Q of t plus 1 is 1. Substitute J is 1, K is 0 and clock as 1. So because K is 0, one of the input is 0, we can say that the output of this NAND gate is 1. Before that, let us give the feedback of Q bar and Q. We can observe that the output of this NAND gate is 1 and here it is Q bar dot 1 dot whole bar, that is Q. So now Q dot Q bar whole bar is 1. So we'll get Q as 1 and 1 will be fed back here. 1 dot 1 is 0. Q is 1 and Q bar is 0. So when J is 1 and K is 0, Q of t plus 1 is 1. Now final case, that is J and K as 1. Substitute all J, K and clock as 1. Give the feedback Q bar and Q. Now it is like Q bar dot 1 dot 1 whole bar, that is Q will get here, and Q dot 1 dot 1 whole bar, Q bar will get here. So now if you see here, Q dot Q bar whole bar is 1. So here Q will become 1, which will be fed here. 1 dot Q bar whole bar is Q. So we'll get Q here, which will be fed here. Now Q dot Q whole bar will become Q bar, that is Q is becoming Q bar and Q bar is becoming Q, which states that it is complementing its previous output. So we say that when J is 1 and K is 1, Q of t plus 1 becomes Q complement of t. So this shows the logic diagram of JK flip-flop using NAND gates. The other way of representing the logic diagram for JK flip-flop is using NOR latch and AND gates. So the function table what we have just now completed we are giving here, and let us get characteristic equation for the JK flip-flop. J bar J, K bar K. So it is like Q 0 1 Q bar. The mapping goes like this. So the characteristic equation J for JK flip-flop is Q of T plus 1 is equal to JQ bar plus K bar Q. This is the information regarding the JK flip-flop. D flip-flop we can give logic diagram in different ways. Here we are giving using NAND gates. Using only NAND gates itself we are having different variations. So that is using 4 NAND gates, this is the way, and using 5 NAND gates instead of NOT gate we can use NAND gate. 5 NAND gates or 4 NAND gates and 1 NOT gate we can give like this. Now if you see here, if I remove this NOT gate, this is R and this is S flip-flop. That is SR flip-flop can be converted into D flip-flop by just giving NOT gate between S and R inputs. And D flip-flop will be having only one input, that is D input, two outputs Q and Q bar. The D flip-flop is very simple such that like whatever the input we give, the same output we will get. D is 0 means Q of T plus 1 is 0. D is 1 means similarly Q of T plus 1 is equal to 1. So from this function table itself we can understand that the characteristic equation is Q of T plus 1 is equal to D. The other ways of representing the D flip-flop is shown here. Now we will see T flip-flop. The different ways of representing T flip-flop is shown here. T flip-flop also will be having single input and two outputs. That is T is the input and Q bar will be the outputs. T flip-flop can be obtained from the JK flip-flop by just connecting J and K together and representing as T. T stands for toggle. That is toggle flip-flop. Toggle is nothing but changing its state all the time. So whenever you give T as 1 and keep on giving clock pulses, the output will be complementing all the time. That is toggles all the time. So when T equal to 0, output is preserving its previous state. When T equal to 1, it is complementing its previous state. So from this function table, we can write the characteristic equation as Q of T plus 1 is equal to T Q bar. When T is 1, it is Q bar. So we write T Q bar plus T bar Q. When T is equal to 0, it is Q of T. So we write T bar Q. So finally Q of T plus 1 is equal to T Q bar plus T bar Q.